Hello everybody. So I thought I'd do this video a little bit different. I got tired of writing everything on paper. I guess because I've been making so many videos recently for all my classes. But anyway, so I have some slides here I've written on my computer, and I want to go through my lesson on these. Okay. So first topics in big picture. All right. So this is about mutually exclusive events and the addition rule. And I say that because if you go about your homework or you, I don't know, if you're reading the book or whatever, you might hear the term mutually exclusive events. Now, uh, let's do this though. That's what the video is about. Okay, those are the topics. But I always think it's nice. I mean, this is from my point of view to think about the kind of questions that we're going to end up answering once we learn all this. So let me give you this example right here. So just about everything we do in our class starts with a probability experiment. And that's anything where the outcome is uncertain or unpredictable or random, okay? It could be drawing a card at random from a deck, or flipping a coin, or asking a survey question to a person where we don't know how they're going to respond, okay? So let's say that we're going to draw a card at random from a standard 52 card deck. Now, one thing that we've already learned is, well, how do you calculate the probability of drawing a jack? And you say, well, how many jacks are there in a deck of cards? There's 4. And then, well, how many cards are there total? There's 52. So your odds are like 4 out of 52. And then you could convert that to a decimal or a percentage depending on what the question was. Now, now that's what we've already learned. Here's where we're going. What would the probability of drawing a jack or an ace be? Okay, well, that's different. It's got the word or in it. Okay, so I've drawn special attention to that word. Or, okay, so not just drawing a jack or drawing an ace, but drawing a jack or an ace. All right, so that's one thing that we'll learn how to do. Or what's the probability of drawing a jack or a spade? Okay, now, so that's what your mind should be drawn to, is when we are learning how to apply the rules of probability, the word or should catch our attention at this point. All right, now, so this is what we're going to learn how to do. Notice I put question marks for the answer because, well, I haven't learned how to do it yet. Anyway, okay, well, StatCat's got something to tell us. So StatCat says, in order to calculate OR probabilities, we first have to know what mutually exclusive events are. Okay, what is a mutually exclusive event? Well, all right, let's learn. Okay, so two events, A and B, are mutually exclusive events if A and B cannot both happen at the same time. All right, so they can't both happen at the same time. So here's an example. We got our probability experiment. Draw a single card at random from a standard 52 card deck. Draw any jack would be one event, and draw any king would be another event. Could both of these happen? I mean, if you drew a card, one card from a deck of cards, could you draw one that was both a jack and it was also a king? That can't happen, all right? I mean, look, here's what the deck of cards looks like. There's 4 jacks, 4 queens, 4 kings, and they're all different cards, okay? So yeah, those events are mutually exclusive because they can't both happen. If you draw one card, it can't both happen. All right. Now there are lots of other examples of mutually exclusive events, but you know, no matter what, you know, they can't both happen at the same time. Okay. Let's see another opposing example. So let's do the same probability experiment. Draw a single card at random from a standard 52 card deck, and say one event is draw any jack and another event is draw any spade. Okay, well, those are not mutually exclusive events. I could draw a single card and they could both happen. How's that? Well, okay, there is this card right here, the Jack of Spades. It's both a Jack and a Spade, all right? So if I was drawing a single card, one card from a standard 52 card deck, it could be such that I drew a Jack, but it could also be such that I drew a Spade, and therefore I could say both of those things happened, all right? Okay, so those are not mutually exclusive events. Now, there are lots of other examples of not mutually exclusive events, but anytime two events could both happen in the manner that I've given you in this example, then that's what we're talking about. Okay, so now let's learn how to calculate the OR probabilities I had at the beginning of the lesson, and we'll use something called the addition rule, okay? So here goes. We'll want to calculate the probability of event A happening or event B happening, okay, in either case. Now, the way that you calculate OR probabilities depends on if the events are mutually exclusive or not. So probability of event A or B is probability of event A plus probability of event B minus the probability of event A and B happening. That's if the events are not mutually exclusive. Okay. All right. Now, 2, what's the probability of event A or B happening if the events are mutually exclusive? It's just the probability of event A plus the probability of event B. Okay. Now, notice that the only difference between these formulas is this one is missing this minus probability of A and B happening. Now, you can use these formulas as they are, but I'd like you to see that they're really the same formula. So say events A and B are mutually exclusive. Doesn't that mean that they can't both happen? So what would happen to this if the events were mutually exclusive? What's the probability of event A and B happening if they were mutually exclusive? It'd be 0. They can't both happen. What's a probability of 0 mean? It means it's impossible. So this formula becomes this one if the events are mutually exclusive. So they're the same formula, but like I said, you could use them the way they are. Okay, so let's see an example. So we're going to draw a single card at random from a standard 52 card deck. All right. Now, my events are A, draw any Jack, B, draw any Spade. Now, if we're going to calculate the probability of drawing a Jack or a Spade, which is what this means, if you were to say it out loud, you say, what are the odds that I draw a Jack or a Spade? Then, well, doing that depends on whether the events are mutually exclusive or not. And we determined earlier in the video that these events are not mutually exclusive. They can both happen at the same time. So here's our formula. Probability of A plus probability of B minus probability of A and B. So let's go through those one at a time. What's the probability of drawing a Jack? Well, there are 4 Jacks out of 52 cards. Okay, then plus, what's the probability of drawing any Spade? There are 13 Spades out of 52 cards, right? So see, here's the Spades right down here, and there's 13 of them. There's 13 of each suit: clubs, diamonds, hearts, spades. Okay, so then minus, what's the probability of drawing a card that is both a Jack and a Spade? That's how I would read that. Well, how many cards fit that description? How many cards up here are both Jacks and Spades? Okay, I think I accidentally pointed to this one earlier as the Jack, but it's this one down here. All right, sorry. So that one, I just moved my picture out of the way. That's the Jack of Spades. There's only one card, or again, I'm sorry, I can't remember now. I think earlier in the video I I said this one was the jack of spades. That's clubs. Okay. But anyway, there's only one. All right. There's only one. So that would be 1 out of 52. All right. So there's our formula. There's each of those probabilities. 4 out of 52 plus 13 out of 52 minus 1 out of 52. And then that turns out to be 16 out of 52, which from there you can convert to a decimal or a percent depending on how you wanted or needed to answer. All right, so let's look at another one. So again, let's say that we're going to draw a single card at random from a standard 52 card deck. And here my events are draw any jack and draw any king. Now these events are mutually exclusive. They can't both happen at the same time, and we talked about that earlier in the video. So in this case, what's the probability of A or B? Or if you wanted to verbalize it, it'd be like saying, what are the odds that I draw a card that's either a jack or a king? Well, the formula for that, for mutually exclusive events, are just the probability of A plus the probability of B. And probability of drawing a jack, well, there's 4 jacks out of 52. Okay, 4 out of 52. Plus probability of drawing a king, well, there's 4 kings, 4 out of 52. That makes 8 out of 52. And we can convert that to a decimal or a percent from there. Okay, so now we've seen one of each. We see what mutually exclusive events are versus events that are not mutually exclusive. And then we did a probability of A or B calculation for each type. All right, now let's do one more question where this time we're given data, because I said a probability experiment, it could be, something like, you flip a coin or you draw a card from a deck, or you survey people, okay? Or you pick people out of a group that fit certain characteristics. Okay, so here's a question where we're given like results of a survey. We start with data, which shows the results of a survey of 1,070 adults that ask if were asked if they favored or opposed a tax to fund education. As you see from the table, some respondents were unsure. Okay, and that's divided into males versus females, those that supported the tax fund or opposed it or were unsure how they felt. Okay, now we got this group, and like that's how both their genders are and their feelings about whether they support or oppose or whatever. So what we'll do is we'll select a person at random from this group of 1,070 people, and the events are as follows. So we got all these people, like they're all mixed up. We're going to pick one at random without knowing how it's going to work out. So event A, the person selected is not unsure. Okay, so that means they knew how they were going to vote, that they either supported it or opposed it. So that'd be like they supported it, here versus male versus female, or they opposed it. That's not unsure. And then B, the person selected is female. Now, those events are not mutually exclusive, right? Could you pick a person at random from this group and they both know how they feel about this, meaning they're not unsure, and they're also female? Well, sure, that could definitely happen. But these are not mutually exclusive events at all. Okay? Look, there are females who are not unsure. So yeah, very easily you could randomly select somebody that fit both of these descriptions. So both of those events could happen. They're not mutually exclusive. Now, what I would like to do is calculate this. What is the probability that you pick a person at random, one person at random, who is not unsure how they feel, they know how they feel, and they're female? Okay, so that would be the probability that they are not unsure. Okay, plus the probability that they are female, minus the probability that they are not unsure and female. Okay, Now that's the formula that I gave you previously for probability calculations with events that are not mutually exclusive. That's that formula. So let's see. Here's this one. What's the probability that that the person is not unsure, that they know how they think? Notice the numbers I wrote down. It's 404 plus 631 out of 1070. You see, supporters. Well, there's 404 people that support. I mean, they know how they feel about this, and there's 631 that oppose. They also know how they feel about this. 404 plus 631. But there's 1,070 total. So those are the odds of just selecting somebody that is not unsure. Okay, so that's probability of event A. And then plus probability of event B. What's that? Probability that this person randomly selected is female. Okay, well up here, let's see. I have hold on just a second. 558. Sorry, I was looking at the wrong thing. There are 558 females. Okay? See, 240, 298, 20 is 558. So the probability of just picking a person at random that's female, there are 558 females out of 1,070 people total. So those are the odds of just randomly selecting a female. That's what probability of B is. Then minus, okay, the probability of this random person that you pick being both not unsure and female. Okay, so let's look up here. How many of those are there? How many people are there that are not unsure but also female? That's what probability of A and B means. Notice I put 240 plus 298. Okay, well, here are the females. There's 240 that support, 298 that oppose. Those are the ones that aren't unsure. Then there's 20 that are unsure. I gotta leave those out because probability of A and B is the probability that the person is not unsure. They know how they feel, but they're also female. So I'm looking at the females row right here, and I'm ignoring the ones that are unsure. So that's how the 240 plus 298 came up. And divided by 1,070 people total. So there's your formula, and the numbers are from the table, but looking at the correct parts of the table and understanding what the and means and what the probabilities are on their own. Okay? Now, doing all the math, that works out to be 1,055 over 1,070, or about, converting to a decimal and a percent, about a 98.6% chance. Okay, now then here I think we've seen a little bit of everything that we might come across with this. Okay, it all starts with knowing if the events are mutually exclusive or not. So if you're having problems working the assignment or whatever you encounter, if you're having problems getting things right, it might be that we need to go back to the very beginning and make sure that we understand if we're correctly identifying whether events are mutually exclusive or not, okay? But from there, the formulas are set in stone, all right? And you might be using the wrong one, or you might be misunderstanding the word "and" correctly, but I think in the video I've covered all the types of cases that you might see, but if you have any trouble, you always let me know.